Welcome to tutorial 19. Today we're going to talk about the simplest type of carbohydrates known as monosaccharides. Before we get to that, just a quick reminder that the notes to accompany this video tutorial are available online through my website. And with that said, let's go ahead and get started by looking at three of the more common monosaccharides first. So D-Glucose is the most abundant monosaccharide in nature. D-Galactose, we're going to see, is one of the monosaccharides found in the disaccharide lactose or milk sugar. And D-Fructose is found naturally occurring in fruits and honey, and because of its intense sweetness, fructose is often used in packaged foods and beverages as a sweetener, often in the form of the highly processed high fructose corn syrup. So we're just going to pick these three monosaccharides to look at while we make some general statements about the structures of monosaccharides. So first thing you might notice is that the monosaccharides all contain just carbon, hydrogen, and oxygen. So I'm going to write that down here as our first general statement. Contain carbon, hydrogen, and oxygen. And although our three examples happen to contain 6 carbons specifically, a monosaccharide can contain anywhere from 3 to 7 carbons. So I'm going to write that down here, 3 to 7 carbons. Now, if a monosaccharide just has 3 carbons, you might hear it more specifically referred to as a triose. If it contains 4 carbons, a tetrose, 5, a pentose, 6, a hexose, so these would all be hexoses, and 7 as a heptose. So again, all of our examples up here just happen to have 6, so I'm going to write a little side note here. Our examples contain 6 carbons, and in fact, they all have the same molecular formula, C6H12O6. So they are all isomers of one another. All right, notice the functional groups contained in our monosaccharides. They're all the same. They all have a number of hydroxyl groups. And over here as well. And they also contain a carbonyl that is either part of an aldehyde or a ketone. So I'm going to write down here, contain several OH groups and either an aldehyde or a ketone. For monosaccharides containing an aldehyde functional group, they are often more specifically referred to as aldoses. So I'm going to write down here, aldose. A monosaccharide with an aldehyde is an aldose. For those with a ketone, ketose. So I'll write that underneath ketone, ketose. All right, notice that all of our monosaccharides are drawn in Fischer projection. We talked about Fischer projection in our last tutorial, tutorial number 18, but I do want to just give you a very quick reminder of how to interpret a Fischer projection. So I'm going to go ahead and erase these bullet points here, 1 through 3. Okay, so in a Fischer projection, remember that all of the intersecting lines are representing a chiral carbon. So glucose has 1, 2, 3, 4 chiral carbons, as does galactose, 1, 2, 3, 4, and fructose has 1, 2, 3. So I'm going to write that here. intersecting lines represent chiral carbons. I'll just write C for carbons. Remember that a Fischer projection is representing a specific conformation of a molecule. In a Fischer projection, all of your vertical bonds are oriented away from you. They're going into the plane of the paper, or in my case, the plane of the white erase board. So these 6 carbons, 1, 2, 3, 4, 5, 6, in this vertical line are going to have a C shape. All the bonds have been oriented so that they are in a C shape, and that C shape is going away from you into the plane of the paper. So I'm going to write that here. All vertical bonds are pointing into the plane, going away from you. That means that all of your horizontal bonds are coming out at you at a 109.5 degree angle. Remember that the horizontal bonds will hug you. We said that back in tutorial 18. They are pointing out at you like they're going to hug you. So I'm going to write that here. All horizontal bonds are coming out of the plane. That is, that they are coming toward you. All right, so when we draw our monosaccharides in Fischer projection, it makes it very easy for us to distinguish between a D and an L enantiomer. In a Fischer projection, a D or dextro enantiomer will have the lowest chiral carbon facing to, with a hydroxyl group facing to the right. Okay, so you already can see that these are all the D enantiomers. The reason that they are the D enantiomer is because they all have the lowest chiral carbon with an hydroxyl group on the right. So I'm just going to circle that for all of these. That is what makes these D isomers, as opposed to the L enantiomer, which would have the lowest chiral carbon with a hydroxyl facing to the left. So very easy to distinguish between the D and the L enantiomer if you have these drawn in Fischer projection. So I'm going to write down here D enantiomers have the OH, the hydroxyl group, of the lowest chiral carbon pointing right, or dextro. The L enantiomers have the hydroxyl group of the lowest chiral carbon pointing to the left. Or Alevo. Okay, so real quick, I just want to point out that the capital D does not stand for dextrorotatory, and the capital L does not stand for levorotatory. The capital D and the capital L simply tell you whether or not the hydroxyl group on the lowest chiral carbon in a Fischer projection is facing to the right or to the left. It does not tell you whether or not that enantiomer is dextrorotatory, meaning it rotates plane polarized light to the right, or levorotatory, meaning it rotates plane polarized light to the left. To determine whether or not an enantiomer is dextrorotatory or levorotatory, you either have to go find a polarimeter and measure it and see, or look it up in a reference book, or find where it's indicated in the name with either a plus or a minus. So you'll see that D-Glucose is dextrorotatory, as indicated by the positive symbol here. So is D-Galactose. But D-Fructose is levorotatory. So don't think that the capital D or the capital L tells you the direction in which the enantiomer rotates plane polarized light. It does not. Only the plus and the minus in the name will tell you that. Okay, so let me label that really quickly before we go on. This means that it's dextrorotatory. Again, that means it rotates plane polarized light to the right. D-Galactose is also dextrorotatory. But D-Fructose, we can see, is levorotatory. That is, it rotates plane polarized light to the left. All right, so we can easily, and I'm going to do this in blue to make it stand out a little bit, we can easily draw L-glucose just by looking at D-glucose here. And let's go ahead and do that. We have probably enough room to do it on this side. So I'm going to draw a mirror image here. L-glucose is the enantiomer of D-glucose. So again, the non-superimposable mirror image form. So I'm going to make my 1, 2, 3, 4 chiral carbons. The aldehyde at the top. And then make sure that these reflect in the mirror image. So OH and H, H, OH, OH here and an H here, and an OH here and an H here, and then our CH2OH. Okay, so this would be L-glucose, and because we already know, because it's indicated here, that the D-glucose is dextrorotatory, we should be able to infer that the L-glucose must be levorotatory. Because remember that two enantiomers will have the same number of degrees of rotated light for rotated plane polarized light, but they will rotate that plane polarized light in opposite directions. So if this is dextrorotatory, this must be levorotatory. Okay, so L-glucose. All right, so we're going to go ahead and erase here, and we're going to go on to slide number 3 and talk about some reactions that will be relevant to monosaccharides. Aldehydes and ketones can react with alcohols to form hemiacetals. I'm going to write that up here. Aldehydes and ketones react with alcohols to form hemiacetals. Okay, so let's just take a look at a generic aldehyde reacting with an alcohol first. So I'll just draw a generic aldehyde with an R group to represent however many carbons it has. And then of course, in order to be an aldehyde, it must have a hydrogen. Okay, so I'll label this my aldehyde. And I'm going to draw my alcohol a little funny over here. And again, just a generic alcohol. Doesn't matter if it's methanol or ethanol or whatever alcohol, however many carbons it has out here, doesn't matter for this generic example. And I'm going to go ahead and put my electrons, my lone pair electrons, on my oxygen there. Now I'm not going to show a full mechanism for this reaction. If you're interested in seeing the full mechanism, you can easily look that up in an organic chemistry book or maybe even an introductory organic chemistry book. But what I'm going to do is I'm going to show you a method that will use curved arrows that I think will help you to just be able to figure out and understand which bonds are breaking and which bonds are forming here, even though it's not the true mechanism and it's not truly the order in which the bonds are broken and formed. Okay, so I hope that makes sense. So the method that I like to use here is to show my partial negative oxygen, this would be a partial positive hydrogen, being attracted to the partial positive carbon of the carbonyl. Remember, oxygen is more electronegative, so it's going to be partial negative here. Okay. Then show the double bond of the carbonyl breaking. Show your partial negative oxygen of the carbonyl being attracted to the hydrogen, which is partial positive, and show the hydrogen giving up this bond to form its new bond to that oxygen. Okay, so what do we get as our final product? So again, this is not a true mechanism, just this is a method to help you understand where bonds are forming and where bonds are breaking. So what you want to do over here when you're trying to draw your hemiacetal product is go ahead and draw the R and the H, because those didn't change. They're still bound to that carbon. Now that carbon is no longer a carbonyl. There is a single bond here to an OH, this oxygen and the hydrogen that it picked up in the reaction. There's a new bond to the OR that was part of the alcohol. Okay, so OR. And a carbon that is bound to both an OH and an OR makes up a hemiacetal. Okay. And this reaction is reversible, so I'm going to go ahead and put an arrow back, and we'll see that when we get to the mutarotation in monosaccharides. All right, but before we do that, let's go ahead and do the same thing here, but for a ketone. So a ketone, oops, let's go back to the black pen. We've got a carbonyl with two carbons, a carbon on each side. Doesn't matter how long the carbon chains are, we don't care what exact ketone it is. Right now we're just showing a generic ketone, but make sure that you don't have a hydrogen, because that would make it an aldehyde. Okay, so write ketone here. And again, I'll show my lone pairs. And again, I'm going to draw my alcohol in that kind of unique way there, with the hydrogen and the oxygen in position to just show this method. Okay, so here's my generic alcohol. Again, doesn't matter if it's one carbon over here or two carbons or three carbons, that's not important. And the reaction is reversible, so I'll write two arrows there. All right, going to the blue pen. And again, this is not the mechanism for this reaction. This is just a method that I hope will help you to see what bonds break and what new bonds form without going through that detailed mechanism for the reaction. So partial negative oxygen attracted to that partial positive carbon of the carbonyl. This turns into a single bond, partial negative oxygen attracted to a partial positive hydrogen, and this bond breaks. Okay, So our product, again, draw the carbon with its two R groups from the ketone. Those didn't change. Those bonds remain unchanged. But now we just have a single bond to an OH. And then we have another bond here that formed to the OR of the alcohol. What was the alcohol here? All right, so a carbon attached to an OH and an OR is a hemiacetal. However, when the hemiacetal came from a ketone and has two carbons here, instead of a carbon and a hydrogen, it is often more specifically called a hemiketal. So I'm going to write that down here. Hemiketal. Okay. All right. Now, when the carbonyl, whether it's an aldehyde or ketone, and the hydroxyl group that's reacting, the alcohol, are within the same molecule, you end up with a cyclic hemiacetal. And that is what happens in a monosaccharide. A carbonyl and a hydroxyl from within the same molecule react, giving you a cyclic hemiacetal. And this is the form in which monosaccharides predominantly exist. So we're going to take a look at that next. So we just learned that an aldehyde or a ketone can react with a hydroxyl group to form a hemiacetal. And we said that when those two functional groups are within the same molecule, you will form a cyclic hemiacetal. And that's exactly what happens in monosaccharides. So let's take a look at how this happens in D-glucose. So what I'm going to do first is take the red pen and I'm going to number all of my carbons. Carbon number 1, 2, 3, 4, 5, and then down here, the achiral carbon down here is 6. Okay. And let's go to the blue pen here. So we remember, or hopefully you remember, from tutorial 16 when we first started talking about cyclic hydrocarbons. You might remember that we said that 5 and 6 membered rings are the most stable. And the reason is because they can accommodate that 109.5 degree bond angle of the tetrahedral geometry. And so we would expect that not just any of these hydroxyls, but specifically the hydroxyl groups that would result in either a 5 or 6 membered ring would be the ones to react. So if we take a look here, carbon 1, there's our aldehyde. If that reacts with the hydroxyl here, we would get a 1, 2, 3 membered ring. Not going to happen. Here we'd get a 1, 2, 3, 4. Not going to happen. If it reacts with the hydroxyl off of position 4, we'd get a 1, 2, 3, 4, 5, because that oxygen is going to end up part of your ring. So that's going to be a 5-membered ring. So I'm going to write over here, if the aldehyde reacts with the hydroxyl of carbon 4, all right, C4, this equals a 5-membered ring. Okay. 1, 2, 3, 4, and 5. Remember, the oxygen's going to end up as part of the cyclic hemiacetal, so a 5-membered ring. The 5-membered ring form of a monosaccharide is called the Furanose form. I'm going to write that in parentheses here. This is the Furanose form. Okay. If the aldehyde reacts with the hydroxyl off of the carbon 5, then we will get a 6-membered ring. 1, 2, 3, 4, 5, 6. Okay, so I'm going to write that here. If the aldehyde reacts with the hydroxyl off of C5. This will yield a 6-membered ring. Remember that those 5 and 6-membered rings are not flat. They are kind of puckered, and that's how they accommodate that 109.5 degree bond angle that is equal to what you see in the tetrahedral geometry. Okay, so the 6-membered ring form is called the Furanose form. Now with glucose, what you actually see the most of is the Furanose form. So we're going to go ahead and show the formation of the 6-membered ring for glucose, not the 5, which you really won't run into when we start looking at the disaccharides and polysaccharides in our next tutorial that contain glucose. All right, so what you want to do, we'll go back to the black pen for this. What you want to do first is lay the Fischer projection on its side to the right. So I'm going to write here, lay Fischer projection on its side to the right. Now, when you do that, notice that all of the hydroxyl groups that are on the right side of the molecule are now going to be pointing down, and all of the hydroxyl groups, in this case there's only one, that are on the left side of the molecule in a Fischer projection, when you lay it down, those are all going to be pointing up. So I'm going to make a little note of that here. All hydroxyls on the right will now point down, and all of the hydroxyls on the left will now point up. Okay, so I'm going to redraw this on its side right down here. So we've got our aldehyde functional group, carbon 1, and then I've got carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 is my CH2OH. Okay, so this one, because I laid it on its side, it's pointing down. The next one is pointing up, and the next two are pointing down. Okay, so you can really see that C-shape backbone now right here. I've laid it down on its side. Okay, all right, so let's go ahead and number these just to help you keep track of where everything ended up. So we've got carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. All right, now, since we're trying to show the reaction between the aldehyde, we're showing the formation of the 6-membered ring, so we're showing it reacting with the hydroxyl off of C5. We want to rotate this bond here so that we put the hydroxyl off of C5 in position for the reaction. So I'm going to draw an arrow here, and let me write the note in black. We want to rotate this bond to position the OH group of C5. Okay, so that's what we're doing here. So I'm going to draw a little arrow here, and the result of that, this is not a reaction. Remember that single bonds rotate freely. We're just taking it out of Fischer projection here. So the result of that will just be a new conformation of the molecule. My aldehyde, carbon 2, carbon 3, carbon 4, carbon 5, and now my OH is pointing here, and my carbon 6 carbon 6 got rotated up. Okay. All right, let me label all my carbons. Carbon 1, 2, 3, 4, 5, 6. Okay. And nothing changed on any of the other bonds. So down, up, down. Okay, this one got rotated, so this one's pointing toward the aldehyde functional group now, ready for reaction. I'm going to go ahead and put my lone pairs just to stay consistent with the method that I showed you earlier. Remember, this is not the full mechanism. This is just a method that I hope will help you remember which bonds form and which bonds break. Okay, so back to the red pen then. Partial negative to partial positive. Double bond turns into a single bond. Partial negative oxygen grabs a partial positive hydrogen, and the bond here breaks. It's just the same reaction that we looked at on the previous slide, forming a hemiacetal, but it's happening within the same molecule. It's going to make a cyclic hemiacetal. Our final product, I'm going to go ahead and write out the C here, just so we keep tabs of this carbon. Connect those there. Okay. This OH goes down, up, down. I'm just copying that right over from here. This CH2OH is pointing up. And then we have an OH here. Okay. Now let me number my carbons again. 1, 2, 3, 4, 5, and 6. And let's do blue here to circle my hemiacetal. Here's my carbon of the hemiacetal bound to an OR and an OH. Okay, so here's my hemiacetal. Now, unfortunately, this is not the end of the story here. I have sort of a skeletal portrayal of this molecule built here. You'll see my oxygen in red and my oxygen of the OH here also in red with the gray hydrogen. And then this is my hemiacetal carbon. And remember, the ring is not flat, so you can see it's kind of puckered here with that 109.5 degree bond angle. I did not put all my OHs in because I thought it would be too busy and difficult to see. What I want to point out here is that on the hemiacetal carbon, in fact, I'm going to just hold on to that hemiacetal carbon here. On this hemiacetal carbon, we have a bond to the oxygen in the ring and a bond to the carbon over here in the ring. And then we have two substituents. I only wrote out one here. We have the OH that came from the carbonyl oxygen, and then we also have a hydrogen on there. This hydrogen here is still there. Now, the OH can point up and the hydrogen point down, like I have in my molecule here in my model, or the reaction can occur such that the result is an OH that points down and a hydrogen that points up. And so there's two different isomers that can form here. They're actually diastereomers of one another. We call them the alpha and the beta form of the D-Glucose. So let me draw both of those. Right down here, I'm going to draw them one on the right and one on the left. Okay, so first I'll draw my OH pointing up. That is on the same side as the CH2OH. Everything else is the same. When the OH is on the same side, pointing on the same side as the CH2OH, that is, they are both pointing up, we say that we have the beta configuration. So this can be called beta D-glucose, or more specifically, because we know that there is both a furanose and pyranose form, this can be called more specifically beta-D-glucopyranose. Which tells you that it is D-glucose as a six-membered ring, six-membered cyclic hemiacetal, with the hydroxyl group on the hemiacetal carbon pointing up in the same direction as a CH2OH. That is the beta form. The other diastereomer, the other anomer, would have that OH pointing down, the opposite direction as the CH2OH of the carbon 6. Everything else stays the same, so down, up, down, okay? And this is the alpha form, alpha D-glucose. Or again, because we know that there is a 5-membered ring form and a 6-membered ring form, let's go ahead and be more specific and call this alpha D-glucopyranose. Remember that the 6-membered rings are the pyranose forms. Okay, one last thing, remember that the alpha and the beta form of the cyclic hemiacetals are a type of diastereomer, a special type of diastereomer relationship called anomers. I'm going to write that down here, if I have room. Let's see, how about over here? The alpha and beta forms are a type of diastereomer called anomers. Okay, that new word there, anomers. All right, last but not least, and then we'll move on and we'll look at one more example for D-Fructose. Last but not least is that in the pure form, the pure crystalline form, glucose and other monosaccharides will exist entirely in the cyclic form, the cyclic hemiacetal form. In an aqueous solution, which is how a sugar, a monosaccharide, will exist within a living organism, they are found in both the alpha and the beta cyclic hemiacetal forms, as well as the open ring, the straight chain form, the acyclic form. And they're found interconverting between the alpha and beta form. And in order to interconvert between those two forms, of course, they must go through this open chain form. So you will actually find D-glucose in an aqueous solution in all three of those forms, predominantly the cyclic forms. But in order to interconvert between the alpha and beta, has to go through the straight chain form as well. Okay. And this can be very important because you'll probably be doing some tests in the lab, testing for the presence, for example, of an aldehyde, presence of a reducing sugar. And it's important to really understand how these molecules exist in that solution. If you're just thinking of D-glucose as existing in these two cyclic hemiacetal forms, then you're not really going to understand why you get a positive test for a reducing sugar. Because you're not thinking about the functional groups that are really truly present in solution. And in solution, you do have some of this straight chain form, which means you have an aldehyde, which can be oxidized. Okay, so it's really important to understand that chemistry and understand how these monosaccharides really exist in an aqueous solution, which again is how they exist in a living organism. All right, let's erase here and go on to one last example of mutarotation for D-Fructose. Okay, so one last example using D-Fructose. I am going to once again number my carbons in the chain. So we've got carbon 1, 2, 3, 4, 5, and this last one is number 6. Now if we get a reaction between the ketone and the hydroxyl at position 5, then we'll have a 1, 2, 3, 4, 5. Remember, the oxygen becomes part of the ring, so 5-membered ring. So let me write that here. Reaction between the ketone and the hydroxyl of C5. That will give us the Furanose form. Remember, that's the 5-membered ring. And if we get a reaction between the carbonyl, the ketone, and the hydroxyl off of C6, that will give us a 1, 2, 3, 4, 5, 6-membered ring. Okay, so I'm going to write that here. Reaction between the ketone and the hydroxyl off of carbon 6, whoops, not 5, 6, then we'll get the 6-membered ring, which remember is the Furanose form. All right, form here. Okay, now we're going to be seeing D-Fructose predominantly in the Furanose form when we start talking about disaccharides and polysaccharides. So I am going to show the first reaction here. I'm going to show the reaction that will give you the Furanose form. So I'm going to show the reaction between the ketone and hydroxyl off of C5. Okay. All right, the steps are identical to the steps we followed previously for D-glucose. You find my black pen here. Okay. First thing you want to do is lay the Fischer projection down on its side to the right. Okay, so I'm going to write that here. Lay it down to the right. And I know I said this before, but just a quick reminder, that means that all of your hydroxyl groups that are on the right side of the molecule are now going to be pointing down. All of your hydroxyl groups that are on the left side of the molecule will now be pointing up. Okay, so let's draw that down here. I've got my ketone, which has a CH2OH. So C1, C2, C3, C4, C5, C6, which is CH2OH. My hydroxyls then are pointing up at C3, down at C4, and down at C5. That's a little bit messy. Okay. All right, I'm going to number my carbons so that we don't lose track of things. 1, 2, 3, 4, 5, 6. Okay. Now we want to show the reaction with this hydroxyl group here. So I'm going to rotate this bond so that my hydroxyl group is in position for the reaction. So I'm taking it out of the Fischer projection now. So we'll no longer have that C shape. This bond will be rotated. All right, so what do I get? Let's draw it right over here. And this isn't a reaction, I'm just rotating a bond. Remember, single bonds rotate freely. I'm just taking it out of the Fischer projection. Okay, so CH2OH. Here's my ketone, carbon number 3, 4, 5. Now my OH is pointing in, and my CH2OH, my carbon 6, is pointing up. These bonds did not change. So put your hydroxyls in there. Okay, oh, go ahead and put my lone pairs. And remember that this is not the mechanism for the reaction. Remember that this is simply a method that I'm going to use to help you remember which bonds are breaking, which bonds are forming. Okay, so we've got our partial negative oxygen attracted to our partial positive carbon of the carbonyl. Double bond turns into a single bond. Partial negative oxygen attracted to the partial positive hydrogen, and this bond breaks. Okay. So forming our cyclic hemiketal. Remember, it's the 5-membered Furanose form, and remember that at the hemiacetal or hemiketal, in this case, the hemiketal carbon, remember that the hydroxyl group can be formed in the alpha or the beta position, so I'm going to draw both. I'll go ahead and do the beta first. It still has a CH2OH, remember it's a hemiketal. And then this is up, this is down, and then we've got our CH2OH. Okay, so this is one form where the hydroxyl is formed in the up position or the beta position. So this is beta D-Fructose. And remember, we can actually be more specific. Most introductory textbooks are not. So that's why I want to write it this way as well. But we can be more specific and we can refer to it as the Furanose form and call it beta D-Fructofuranose. Okay. Let's do the alpha form down here. So again, a 5-membered ring, that's pretty messy, sorry. Okay, and this time the OH points down and the CH2OH must then point up. Got our OH, up, down, and everything else is the same, CH2OH. Okay, so this is our alpha because the OH is on the opposite side of the CH2OH. CH2OH points up, the OH points down. This is alpha D-Fructose. Or more specifically, this is alpha D-Fructofuranose. The 5-membered ring form. All right. So we're going to go ahead and end here for tutorial number 19. I know there is one more slide, slide number 5, but all it really shows is just a foreshadowing of the monosaccharides that we're going to see in our nucleic acids, ribose and deoxyribose. So if you want to take a look at that, great. Otherwise, we're going to finish here, and I hope that you will consider tuning into problem set number 19. Thank you very much.